please ask your questions on the Slack channel. And the first speaker is Nuria Miret Roig. I hope I pronounced correctly. Can you hear me?
Yes, I do. Can you hear me?
Okay. Can you share your slides, please?
Yes. Okay, so I would like to start by thanking the organizers for inviting me today to present our recent work published in Nature Astronomy, which is about the discovery of a rich population of free-floating planets in Upper Scorpius, and which has been possible thanks to the joint efforts of all my collaborators listed here, and also thanks to the large data sets that we used, which include many images from the wide field cameras at CFHT. So today I will mainly focus my talk on explaining first the research that led to the discovery of this rich population of free-floating planets, and then I will try to explain how we used the mass function as a parameter to constrain the star formation theories of these free-floating planets. So for those who might not be familiar with free-floating planets, those are planetary mass objects of less than 13 Jupiter masses, which are not bound to a more massive object, but instead are roaming into the galaxy. So those are the lightest products of star formation, and they are thus highly sensitive to dynamic interactions. And this makes them excellent candidates to study the initial conditions of star formation. So while the first floating planets have already been discovered for the past more than 20 years, currently there are still missing large samples of these objects that allow us to study their origin and properties. In fact, there are several theories that have been proposed to explain the origin of free-floating planets. For instance, it has been proposed that they could form by core collapse, that's to say similar to low-mass stars. It has also been proposed that they could form in protoplanetary disks, so in planetary systems like exoplanets, and then they could be eventually ejected, for instance, due to a passage of another star close to this planetary system. Then we can also think of a scenario where several cores are accreting material from the same gas reservoir. If there are interactions between these cores can end up with the ejection of a core that eventually will not be able to accrete enough material to become a star, and instead it will become a substellar object. And finally, also at the vicinity of very hot massive stars, the strong stellar winds of the stars can evaporate the outer layers at the envelope of an accreting core, and this core will eventually also become a substellar object, not being able to accrete enough material. So all these mechanisms are proved to form free-floating planets, and currently the question is which is the mechanism that dominates, or which are the relative contribution of all these mechanisms to the final population of free-floating planets. And to study this, so we propose to use the initial mass function. The initial mass function basically is the mass distribution of stars right after a stellar burst. And currently with Gaia, it is relatively easy to study the stellar content of this mass function, because thanks to the excellent precisions in the astrometry of Gaia, we can relatively easily identify samples of coeval stars and then determine this stellar mass function. However, the majority of substellar objects escape from the Gaia detection limit, and then we need ground-based images to detect these substellar objects. This is especially true in star-forming regions where the objects are still embedded in the paramolecular cloud, and then the high levels of the extinction make that those objects are undetectable by Gaia, which operates in the optical. On the contrary, if we combine Gaia with infrared ground-based images, then we can detect these objects and study their properties. So this is how the Cosmic Dance project was born. This is an ERC project by Hervé Bouy, my PhD advisor. And the aim of the Cosmic Dance project is to provide the observations that allow us to map star-forming regions in the solar neighborhood. Then we use these catalogs of stars to identify the young stellar objects, members of these young associations, and making a special emphasis on the low mass stars and substellar objects. And then we finally use these samples of young objects to study their formation and their early evolution. So now with this slide, I show two of the images that we obtained in the Cosmic Dance project, one in a high extinction area and another image which is taken from a low extinction area, and where we have identified with these yellow circles the Gaia detections. And it is very clear that many sources that are easily detected in our images escape from the Gaia detection limit, and those are crucial if we want to study substellar objects. Now, with this image, I would like to present you the region in which we search for these free-floating planets. So this is a region which comprises 170 degrees squared in the sky, and which encompasses the region of Upper Scorpius. This is a young OV association which has an age between 5 and 10 million years, and where the majority of gas is already vanished, facilitating a lot the identification of young stars. In the same image, we also see the region of Eucus, which is younger. It's still forming stars, but there is a lot of gas still, and this makes it very difficult to detect young stars in this area. So we basically carried on our own observations of this area, and we also queried all the public archives to collect the largest amount of image possible, and eventually we collected and analyzed around 74,000 images taken over the past 20 years. This large time span is very important because we are interested in measuring both the photometry but also the proper motions. So the larger the time span, the more precise the proper motions are. Then these images come from 18 different instruments, among which there are 3 CFHT instruments, which have a very important contribution, as I will comment now. And also, just to give another idea of the size of the data that we analyzed, the number of individual source detections in our images is comparable to the size of the entire Gaia catalog. So in this context, the CFHT images were crucial, and each of the CFHT cameras that we use had a different important role. For instance, VIRCAM, which operates in the infrared, is very important to detect sources in regions where there is still extinction. But not only this, but also the free-floating planets are ultra-cool objects, and thus they are brighter in the infrared than in the optical. So this was very important also to detect these free-floating planets. Then MegaCam provided us with one of the deepest optical images in this region, and also it has a large coverage, which was very important for our study. And CFHT 12K was very important because it constitutes the oldest epoch in our images, and as I have just mentioned, this is very important for the measure of proper motions. So to summarize, wide field images are key for our study, and in particular, the ones taken at the CFHT, they are crucial because they provide us also with this magnificent seeing that is at the CFHT. So then we combined all these images, and as I said, we measured the position, proper motion, and multiband photometry for 26 million sources in this area. And we combined these observations with the Gaia catalog. Here I compare the precision in proper motions as a function of magnitude, And the importance of the dense image here is that we still can measure the proper motions 6 magnitudes deeper than Gaia with relatively good precisions. And these measures are fundamental to identify these ultra cool objects. So now what I'm showing you is one of these images that we produced and compiled in this region. And I would like to ask you a question, and this is, what do you see at the center of this image? This will certainly depend on the quality of the projector that you have and how clean is your screen. But the point is that you should see something here at the center, and it is a free-floating planet. So one of these free-floating planets that we have been able to detect. And the reason why I show this image is that it is still astonishing to me that we have the capabilities now of detecting such a faint red tiny little dot. And not only this, but we are able to measure the proper motions with a precision enough so that we can identify this object as co-moving with the rest of Scorpius, Upper Scorpius. So as I was saying, we combined all the measurements of proper motion and photometry in the sources we detected in this area, and we were able to detect 3,500 members. And from those, between 70 and 170 of which are free-floating planets, and those are the ones indicated with these red circles. As you can see, they are more or less spread all over the region. So some of those are part of Upper Scorpius and others are part of Ophiuchus. Then what we did is we used this large new sample to first obtain the magnitude distribution. And the large size of the sample that we have allowed us to have really small statistical uncertainties in this magnitude distribution. And then we can start to study the details in this function. For instance, I find particularly interesting this dip at planetary masses, which is one of the first time that it has been observed, and certainly poses new questions regarding the origin of all these free-floating planets. For instance, it could tell us that different formation mechanisms are dominant at different masses. Then what we did is we converted individual magnitudes to masses, and we also measured the mass function. This is the function you are seeing at the bottom plot. And now in this mass function, we first can see that at high masses, this is compatible with the Salpeter mass function. This is expected and observed in many other star-forming regions. But the most interesting part of this function, in my opinion, is regarding the planetary masses. First of all, I want to comment that we measured a very low contamination rate for these free-floating planets. This is based on a spectroscopic survey that we will publish very soon, and that it just reinforces the fact that the majority of objects we detected are indeed members of this association. So then what we did is we compared our observations with models to try to understand the origin of these free-floating planets. Basically, what we did is overplot the results of numerical simulations, which mainly form free-floating planets by core collapse. And by comparing the results of these numerical simulations to our observations, it is evident that we observe many more free-floating planets than what it is predicted from these simulations. And then what we wonder is basically which is the origin of all these free-floating planets. Well, so this certainly is an open question, and many more studies and follow-up studies are needed to finally answer. But we believe that what these results are telling us is that core collapse alone cannot explain the entire fraction of free-floating planets that we are observing, and we propose that ejection from planetary system must also have a very important role in producing free-floating planets in this region. So to summarize, it's probably a combination of both mechanisms, what we are seeing here. And I will just finish with a summary of what I have just been explaining. Basically, I presented the first large homogeneous sample of free-floating planets in the region of Upper Scorpius. I also mentioned that wide-field cameras at CFHT have been crucial for the discovery of all these free-floating planets. And the fact that we have now this large homogeneous sample allows us to start to wonder about the origin of all these objects. And we believe that to explain their origin, we have to combine different mechanisms, and we propose that at least core collapse and ejection from planetary system must have important contributions. Also, I mentioned that with a spectroscopic campaign, we confirmed a low contamination rate in our study, which just makes our results much more robust. And finally, these targets are excellent to investigate many more properties of these exotic type of objects, like their atmospheres, their diffraction, binary fraction, which will tell many more about their origin and properties. So thank you very much, and I will be happy to take any questions if there may be.
Thank you very much, Nuria. And by the way, congratulations for the prize that you got for your PhD on this subject. Questions in the room? Yes.
I've got that. Oh, thank you. So this is from Jerome Bouvier. So Jerome asks, mass is deduced from luminosity. How reliable is the mass luminosity relationship in the free floating planet range?
Yeah, that's an excellent question. And I think I have a backup slide. Wait. You are seeing the slide, right?
Yes.
Okay, so so here basically you are seeing a color magnitude diagram of where I am overplotting all our targets, which are both the black and gray dots here. And there you are also seeing the evolutionary models at 3 and 10 million years. And what is evident is that this changed a lot. For instance, an object of 10 Jupiter masses at 3 million years would be placed here, and only 7 million years later, it will have cooled down until here. So beyond the uncertainties on the models, also if we have an uncertainty in the age, which is the case in this case, this also induces an uncertainty on the final mass. But then, so what we did is to try to be conservative, we computed the mass function, assuming first that a very optimistic case in which all the sources have 3 million years of age, and then another case more pessimistic in which all the sources are 10 million years old. And we believe that the result should be somewhere in between. And this is why here, when I show the plot of the mass function, this upper and lower envelope correspond to the cases in which all the objects would have 3 million years and all the objects would be 10 million years.
Thank you.
Answer the question.
I have a question. Did you compare your results with the free-floating planets that are detected by gravitational microlensing about the mass function?
I think so. Here it is a bit complicated to the comparison because the methods are very different. So I would say that in general, the fractions that we expect are compatible within the uncertainties. But the difference is that with microlensing techniques, it is very difficult to do a follow-up afterwards because you just detect the planet at the moment you see the microlensing event. Whilst in our case, we know precisely the position of the planets, and then we can afterwards follow up with the spectroscopy and be able to characterize them and hopefully eventually have better, for instance, better mass precision for each of them, but also all kinds of other follow-up studies.
Okay, let us thank again Nuria.
Okay.
And the next speaker is Olivia Lim. In